Okay, so I hope you can see my screen now, my presentation. All right. Yeah, so my name is Jan Nitzbon, as Christina just said, and yeah, I'm quite happy to have the opportunity today to give this talk to you, and it's nice to see that there's so much interested in this topic. Yeah, so the title of my talk, How do Ice-Rich Permafrost Landscapes Respond to a Warming Climate? Yeah, that's mostly the work which I've been doing for my PhD, and just briefly want to mention my colleagues, which are written down here, which contributed to this, and also want to thank Julia, who is joining today. Yeah, so my background is actually in physics. After that, I switched to the Alfred Wegner Institute to do a PhD there for the last couple of years. And yeah, Christina just mentioned it. I recently submitted my thesis on mostly numerical modeling of yeah, the dynamics of ice-rich permafrost landscape under climate warming. I would like to start off today with giving you some impressions from the field sites I've been working on in Northeast Siberia. So more precisely, it's the Lena River Delta. And I just want to show a couple of pictures now from an expedition I participated in 2017, in the beginning of my PhD, which was yeah, very helpful for me to get as a modeler used to get a feeling for these landscapes, let's say. So what you can see here, for example, is an old Yadoma landscape with an exposure of massive ground ice under the surface. You have a lot of local degradation features related to the ground ice, which is there, like these thermokarst gullies. And you also have in these lowlands these typical polygonal tundra landscapes, ice wedge polygons of different types. I hope most of you, or I guess because you're interested in permafrost, you're sort of familiar to ice wedge polygons. So we have this low-centered polygons, which are actively accumulating ground ice in these cracks between the polygons in form of ice wedges. But then in these landscape, we also have so-called high-centered polygons, and these are actually showing signs of permafrost degradation, like these standing water in these troughs between the polygons. So I'm showing you these pictures mainly because yeah, this expedition there gave me quite important insights into these landscapes, and I want to mention mostly two. So the first thing is that there is a lot of heterogeneity in these landscapes, many small scale features, which one can see when one just walks around there, like in the topography and the hydrology and so on, but also in the subsurface. And the second point is that yeah, the degradation of permafrost, which we see, is mostly occurring locally, like it's not necessarily a widespread phenomenon, but we do see these local signs of permafrost degradation, and they are always related to the presence of excess ice in the ground. And this is more commonly referred to as thermokarst. So more conceptual view of these landscapes, which evolved in the past in very diverse way, is shown here. What is essentially supposed to show is that we have, yeah, quite heterogeneous landscapes on different scales, and that these ice wedges, which are indicated here, these white tooth-like shapes, they are kind of omnipresent. So you hardly have parts of the landscapes where you would not find these bodies of massive ground ice. And yeah, this accumulation of these ground ice is really a key driver of the landscape's dynamic in this very cold permafrost environment. And yeah, ice wedges, there are the most dominant type of excess ground ice. And the question for my research then was actually to investigate in how far the presence of these ice wedges and the ground ice preconditions the future evolution of these landscapes under the expected warming of the climate in the Arctic. So to give a more precise research question, it's also the title of the talk: how do ice-rich permafrost landscapes in this area respond to a warming climate? And I investigated this in terms of the general evolution of this landscape, like the landforms and how they are changing, then the more quantitatively in terms of the degradation of permafrost, how much permafrost would thaw under different scenarios. And I also looked into carbon pools, but I have to say already at this point that I did not do any investigations into greenhouse gas emissions or the permafrost carbon feedback. I kept to a more physical perspective on these landscapes. And then a second, more like a sub-question to this which I'm addressing is which feedback processes are important and are involved in this landscape evolution. And this can be different physical processes like hydrological or geomorphological processes, but it's also interesting to look into ecological feedbacks. And yeah, the main tool, I think I mentioned it already, which I used is, or which I'm also interested in, is using numerical modeling. So, I forgot to mention this. So these are, it's just the first paper kind of where I introduced this approach I took in my PhD that was published in 2019 in the Cryosphere. And then there was a recent paper in Nature Communications where I used this approach to look into future changes. And now I want to continue with with my methodological approach. So yeah, as I said, I'm interested in modeling. And if we want to understand if we want to project what might happen under warming climate in the future, then we kind of necessarily need to use numerical models. And what one could use is, or what's often done is to use Earth system models or the land surface components of these models, which are referred to as land surface models. And this picture here, or this sketch, is intended to indicate how the land surface is represented within these models. And so you have quite large grid cells that are typically, and you have homogeneous landscapes, representations of the landscape, and only representation of vertical processes. But what you don't have is, and that's, if I go back to the motivation from the pictures which I showed you in the beginning, you don't have any representation of excess ground ice in these models. And typically you also don't have any lateral processes which are related to these small scale features in the landscape. So what I did is then going for a more dedicated permafrost model, which is the CryoGrid 3 model. This model has the advantage that one can represent the heterogeneity of the landscape using what's called a tiling approach. That was published already before I started. For my application, which, as I said, is mostly related to these ice wedges and the ice wedge polygons in these landscapes, I developed this tiling approach so that the landscape is represented mainly via 3 different tiles, which correspond to the polygon centers, the polygon rims, and the polygon troughs. And each of these tiles can be different in terms of their subsurface stratigraphy, but also the surface elevation as it's indicated here. As a second point for this cryogrid model is that it does have an excess ice scheme. So in the model, we do have the possibility to assign cells of the model domain a certain excess ice content. And once these cells thaw, the ground would start to subside and this excess water would be pooled upwards, leading to ground subsidence as it is observed in the field. And finally, that's mostly what I've been working on in my PhD is the model has now an implementation of lateral transport processes. And these are different ones. So we do have a lateral transport and redistribution of snow in the winter season, lateral transport of water on small spatial scales, and of heat. And then what has been recently added is also a lateral transport of sediment, which I will also talk a bit more on later. And these lateral processes all that's kind of the hypothesis of my work, that these are exerting strong feedbacks on the landscape evolution and permafrost thaw. Okay, so I did several simulations for a site in the Lena River Delta under different climate warming scenarios. So I did 2.6, 4.5, and 8.5 runs. I also, in these simulations, varied the excess ice content, 3 different amounts, and that's in a way related to the different landscape evolution in the past. So where you have parts of the landscapes which have not been degrading for since the last glacial period, there you can have very, very high excess ice contents. But other parts where there has been thermokarst activity in the past, like formation of thermokarst lake, then drainage afterwards, there you can have also very low excess ice contents. And then one important thing which I also varied in these simulations are the hydrological boundary conditions. And there I looked at 2 extreme cases, which is simulations under water logging on the one hand side, where essentially no water is allowed to drain from the model domain, or at least it's very limited. And on the other hand, an extreme case where the drainage from the polygon troughs is very efficient. You should maybe keep in mind these 2 extreme hydrological cases. In addition to this, I did some reference runs where I did not look into any lateral processes or excess ice. I also did them with cryogrid with the same forcing, and they are supposed to represent how permafrost would typically be represented in a land surface or Earth system model. To not make this presentation too long, I decided to limit what I show next to a few cases here. So I will only show the case with medium excess ice content for the more stronger warming scenarios under the 2 hydrological boundary conditions. So first, I want to show you some pictures how this landscape evolution is simulated in this model setup. So basically the simulation period is the 21st century from the year 2000 to 2100. And we start off with low-centered polygons. They have intact, undegraded ice wedges underneath. On the top left here, you see how this looks in the model world, kind of. So here is shown 2 ice wedges and a depressed polygon center in the middle. And now if we subject this initial landscape to this strong 8.5 warming scenario for 100 years, then we can see, yeah, quite an interesting evolution of the landscape. I will only show the final configuration of the landscape by the year 2100 now, and this is shown here. So if you compare the top to the bottom, you will see that the surface above these ice wedges subsided, so the excess ice melted, and the landscape transitioned from low-centered to high-centered polygons. This is the case for efficient drainage. So there, in this resulting landscape, there is no surface water remaining anymore, but it looks quite different if we do the simulation under different boundary conditions. Oh, sorry, I forgot to mention this. So these high-centered polygons are actually features which can be observed at the field sites already today, but only very locally. So these high-centered polygons are not very abundant there in the Lena River Delta, but we do see locally features which are quite reminiscent of what's modeled. Now for the waterlogged case, we start off basically with more or less the same landscape configuration, low-centered polygons. And if this is now, this system is now driven for 100 years by the strong warming scenario, and in this case the drainage of water is limited, then it results in this configuration down here, where you see that a water body evolved. It's about 2 meters deep, and underneath, indicated here in this dark brown color, is a region about 3 meters deep, which is permanently unfrozen. It's referred to as thallic. So it's a quite different configuration of the landscape compared to the well-drained case. And also here we see locally features in the landscape which are reminiscent of this. So this is an older thermokarst lake which evolved in the past. But I just want to point your attention here towards the fact that these high-centered polygon features, which are which have been simulated to be at the ground bottom of the lake, that they are also visible in these pictures. So overall, this gives us confidence into that our model here is not reproducing any like unrealistic cases, but that these simulations really correspond to situations of permafrost degradation which can be observed in the reality. Now I want to give a more quantitative picture in terms of permafrost thaw and degradation. I'd first like to show 2 simulations of this reference case without any excess ice, without any small-scale lateral processes. So what we see here is that the active layer, so the maximum thaw depth every year, increases in the simulation period from the year 2000 to 2100. The colors here indicate the ground saturation level, so it's fluctuating a little, but parts of the ground are saturated, parts are not saturated. And yeah, you see that the active layer depth increases in both cases, but by the end of the 21st century, even under the 8.5 warming scenario, the thaw depth is still less than 1 meter, and we still have more or less intact permafrost. On the other hand, if we now look into the case with simulations with the representation of excess ice and heterogeneity, we see a quite different picture. First, I would like to show the 8.5 case with the stronger warming. Under the well-drained case, you see that around the year 2060, the ground starts to subside, while at the same time the active layer is increasing more, or is deepening more rapidly. So that by the end of the simulation period, we see ground subsidence of a half a meter or almost to 1 meter, and the absolute level, like the permafrost table, lowered by more than 1 meter to almost 2 meter depths.
I'm sorry, Jan. This is for center of polygon or for the trough?
That's a good question. This is the area weighted mean of the 3 tiles. So it's a mean. Is it clear?
Yes, but it will be interesting to, and you have this ability to show separately for trough and for the center.
Yeah, I don't have it prepared, but I could do those plots for sure. Yeah, then in the waterlogged case on the right-hand side, you see that this degradation is even much faster. We have ground subsidence also starting around the middle of the 21st century, reaching depths of more than 2 meters on average. And the maximum thaw depth increases down to, or the permafrost table lowers down to almost 6 meters. So essentially what we see in this case is substantial degradation of permafrost, which is much larger than in the reference case without excess ice. On the other hand, if we look into the more moderate warming case, the 4.5 scenario, we see that for the well-drained case, not so much is happening. It's hard to see it here, but actually there's a little bit of ground subsidence. So we do have some excess ice melt, but the thaw depths only increase slightly. And in the waterlogged case, we do see that also excess ice melt and thermokarst is starting around the year 2060, and it goes on. But then, as opposed to the 8.5 case, where this is accelerating and going faster and faster, now it's actually slowing down. And in the final 20 years or so of the simulation period, we hardly see any excess ice melt, and the permafrost thaw rates go down and the landscape stabilizes again. And the reason, or I would like to say a few more words on this stabilization versus the positive feedbacks and so on, the accelerated degradation. So there are different feedbacks processes involved. First, for the stabilization, which we just saw in the 4.5 case, we found out that this is mostly attributable to the lateral transport of sediment. So this was a process included in these simulations. And for this, I would like to show this plot here where the evolution of the soil surface altitude for the centers, rims, and troughs is plotted separately. So as you can see, after around here, we see that really there is a very fast subsidence of the troughs where the ice wedges are located, and the soil surface altitude lowers by almost 1 meter within quite short period of time. But then quite soon after this rapid degradation phase, there is sediment deposited in the troughs, and this is actually because the gradient between the rims and the troughs increases. So this gives rise to lateral erosion, and this then causes sediment to deposit in the troughs, causing the soil surfaces to come closer to each other, and it serves as a kind of an additional protection through ice-poor material to the ice wedges. And then by the end, we have this stabilized case with new equilibrium active layers and the ice wedge layers protected from thaw. In addition to this lateral sediment transport, our simulations also showed that generally drainage of the landscape is acting as a stabilizing factor, which is, I think, a mostly well-known thing. And then we have, on the other hand, the destabilizing mechanisms. And it's also a lateral process, which we found to be very important here. That's the lateral snow redistribution. So when we have these subsiding troughs, then these depressions will cause an additional accumulation of snow. This acts as an additional isolation in winter and keeps the soil warm in the troughs. And this is a positive feedback on thaw. So that's why we see this initial acceleration of degradation rates in the troughs. On the other hand, water impoundment, in contrast to drainage of the landscape, is generally a positive feedback. This is due to increased ground heat fluxes and increased thermal conductivities in the active layers. So once we have ponding of water, then this will most likely lead to faster degradation than in drained cases. Okay, then to roughly summarize these different warming scenarios. So what our simulations at least suggest for this region is that under the moderate 4.5 scenarios, these stabilizing feedbacks are at some point dominating the destabilizing ones, and that at least for this simulation period, we end up with a landscape which has some degradation going on in between, but which ends up in a more or less stable state, while in the very strong 8.5 emission scenario, the stabilizing processes can't keep pace with the destabilizing feedbacks, and we see an acceleration of permafrost degradation, which would go on beyond the end of the simulation period. Okay, then I would just want to say also a few words on these carbon pool vulnerabilities. So what we also did for this last paper is to roughly assess how important this process is at a larger scale. So we mapped these lowlands where we are confident that we have the presence of these ice wedges of different types, like Yedoma deposits and drained thermokarst lake basins, and so on. So we mapped this for a larger region in northeast Siberia, and then just did a rough calculation of how much carbon would be subject to thaw under different warming scenarios. And what we found here is that actually for the very low warming case, the 2.6 scenario, it does not matter much whether we take into account the excess ice or not, because the active layers don't increase that much that these ice-rich deposits would melt. And with increasing warming rates, we see that the excess ice and the thermokarst processes become more and more important. And in the most extreme warming case, the 8.5 scenario, there's actually a very huge spread here. So this corresponds to these simulations under different hydrological conditions. This is, one can say, is the uncertainty which is still there in our simulations. Under the most extreme case, we would see up to more than 60 gigatons of carbon additionally subject to thaw in this area, compared to the beginning of the year 2000. And yeah, the other point I mentioned already is that this spread between the two hydrological conditions, that this is really becoming stronger with stronger warming scenarios. So that means our kind of the uncertainty about the future permafrost degradation is increasing with stronger warming scenarios. Yeah, and with this, I'm already coming to the end of my presentation. So I hope that I've been able to convince you a little that this modeling approach with the cryogrid model is really an effective way to investigate this type of ice-rich permafrost landscapes, as it takes into account the heterogeneity, lateral fluxes, and ground subsidence. Then we also saw that the presence of this ground ice generally leads to an really increased overall degradation, especially under the stronger warming scenarios. Then lateral processes like the lateral transport of snow and of sediment are really exerting crucial feedbacks, which are typically not taken into account by more simplistic one-dimensional approaches. Yeah, that's the last point. So the large-scale land surface or earth system models, they really lack key complexity of permafrost terrain, which precludes them from realistically projecting permafrost thaw under climate warming. Okay, yeah, then thanks a lot. And I also prepared some questions for a potential discussion afterwards. So I would be happy to hear about your experience on thermokarst features, maybe from field sites where you are working, whether you see recent changes or trends already now, which might also be investigated with such models. Then the second point would be to hear your opinion on this, the hydrological response of this landscape. So this is really something which I'm very curious about, which pathways of this landscape evolution are more likely, draining or drowning, one could say. And finally, what do you think is still missing from the approaches which I presented? Thanks a lot.
Great, thank you. That was really interesting and very useful. We have about 6 or 7 minutes left for discussion and questions. I believe there's another meeting happening right on top of the hour, so we have to really close it when the full hour is over. Feel free to ask a question now.
Looks like Julie has her hand raised.
Great, yeah, go ahead.
Yeah, nice. Hang on, I'll turn off my air conditioner. I have background noise. I didn't quite understand what climatology was used to drive the different models from the beginning in your cryogrid. Obviously you have the scenarios, but I mean, what kind of regional climate model or global climate model did you use to drive the climatology out to 2100?
Yeah, so for this, the forcing data set we used that has been used in other studies before, and it's based on meteorological observations from the field site in the Lena River Delta. So this kind of gives the climatology, and this has then been then anomalies from I think it's CLM model projections have been applied to this data set to generate the forcing data. So it's more reflective, I think, of the conditions or the climatology in the Lena River Delta, but for this large-scale upscaling, we assume that the variation due to the anomalies from the emission scenarios are larger than the variability within the region. Does it make sense?
Okay, thanks.
And I see Kathy Wilson has her hand raised.
Yeah, so this is Kathy. Great work, Jan. It's really pretty exciting. I just wanted to ask, one thing I've been really interested to see is to have a model that has this kind of level of physical representation draped over, like drape a big piece of the landscape over either a slightly convex underlying topography or a slightly concave underlying regional topography without setting the boundary condition of waterlogged versus water drained, and explore how the landscape would evolve. It seems like, I mean, it's pretty clear that in certain areas, as you show, that the high center polygons seem like they've been there a long time, and they sometimes are in slightly more convex pieces of landscape than some of the more lake-rich areas. Anyway, it'd be great to see if your model could evolve and which directions it would evolve if you just draped like a set of beginning polygons across those two kinds of general features.
Mm-hmm. Yeah, it's an interesting comment. So I think this type of model is really flexible. One can really set up different geometries in the landscape, yeah, reflecting such, let's say, toy cases where one would just do experiments like this. Yeah, I don't have a good answer on what would come out of this, but what's maybe related to this question is also how far the larger scale lateral transport processes like the hydrology over larger parts of the area of such polygonal terrain are need to be taken into account. And yeah, this is actually I investigated this in the final part of my PhD, where I also looked into mesoscale hydrological transport processes, and yeah, that was quite interesting because they could see that one can actually have transitions that some parts of the landscape would initially form thermokarst depressions and water impoundments, but then later drainage channels can evolve and reverse the picture again. So it's getting more complicated if we go to larger scales, actually.
Anyway, thank you. That it's something that would be fun to explore, and hopefully we'll be able to maybe reach out and do that with you at some point in the future. Great
Yeah,
work.
I would be happy to. Thanks.
And Vladimir?
Yeah, yeah, and that's a great presentation. I have a short question and kind of reflecting this number one of your open discussion thing. So the question is, what is the, in general, permafrost temperature in this region you're working?
Currently, we have temperatures at the depths of the zero annual amplitude about -9 degrees, but we have quite strong warming trends of about, oh, no, I don't want to say something wrong, like, I think almost more than 1 degree per decade.
Per decade, okay, thank you. And second, that's you ask about field experience. So we have a great experience about looking actually observing these changes, what you're modeling in high Arctic in Canadian archipelago, where permafrost temperature is actually -14, -15. So we published this paper, you're probably familiar with that, last year, I think. And so it looks very, your results look very kind of similar to what we observe. Only thing is that we were very surprised that it could happen. You don't have to wait to the end of the century. It happened right now in a very cold permafrost, and it took about just 5 to 6 years of anomalously warm summers to start this process. And that's our case is about good drainage, you know, this kind of thing. So because it's on a slope.
Mm-hmm.
And it's massive formation of high center polygons in that area. So not just one small area like you showed in your photo, but or map, but it's really massive. It's pretty much everywhere around you.
Yeah, yeah, that's a good point actually. So it's also what we see in our simulations. Once this degradation starts, then it's kind of an self-enforcing process which goes on, and the timing when it starts, I think that's really a hard thing to project because it really depends on the location of the ice ridge layers in the ground. And this is, I have to admit, also a quite strong uncertainty. So in these simulations, we used a lot of field data from the overall region to get a kind of representative cryostratigraphy. But for an individual site, it can look different. And then the timing when this fast degradation.
Yeah, in our case, the top of the ice wedges were just below the active layer depth.
Yeah, yeah. And I think in our simulations we had like a protective layer of maybe 20 centimeters or so.
Mm-hmm.
That's because that gives the delay.
Yeah, it sounds realistic.
Well, I think unfortunately we have to end here. Thank you so much for your questions and for the presentation. I'm sure people can just email Jan with further questions, and the recorded webinar will be posted on the ARCUS website. And our next webinar, I believe, is September 8th. And we will have a presentation, I think, on the protection of permafrost soils from thawing by increasing herbivore density. So an entirely different topic, but hopefully we can also engage you to participate there. Thanks a lot for tuning in today. Have a good day.
Thanks, everyone.
Thanks.